we were discussing Boolean logic and Boolean operations, right? So we discussed different kind of Boolean operators and also said that traditionally there are 5 different Boolean operators. That is these 5: and, or, not, implication, by implication. But all these 5 can be reduced to just 2, like and not, or even or and not. Okay, anything is fine. And we defined the remaining Boolean operations using these 2 operations. All right. And I would like to mention one more thing, that you may see this kind of notation. You already know this, P implies Q. But you may also see this kind of notation where P bar Q. Okay. So both are not same. This is called implication, whereas this is called inference, and both are not the same. In case you have any doubts, please ask in the chat. Yeah. So this is one single statement. Okay, if P then Q, it is not 2 statements. All right, whereas this is 2 different statements, and the truth value of Q depends on the truth value of P. Okay, so this is similar to the syllogism examples I gave. All men are mortal, Socrates is a man, therefore Socrates is mortal. So there are 2 premises and 1 conclusion. So there the method is inference. So this is that method. Okay, this is like one statement. It can be like all men are mortal. That's all. It is not saying all men and then hence mortal. No, it's just saying if someone is a man, he is a mortal. That's all. This is not saying anything more. So let me give you an example. You might have heard of these terms, modus ponens and modus tollens, right? So if P then Q, suppose you know that statement if P then Q, it is not telling us anything about whether P or Q are occurring right now or not. All right. For instance, if you take a statement like if there is smoke, there is fire. All right. Now it's not necessary that there should be smoke now. There may be smoke now in front of me, or there may not be smoke. But if there is actually smoke in front of me, then using these 2 statements, that if there is smoke, there is fire, and right now in front of me there is smoke, hence I will conclude that there is fire. All right. So for that, if there is smoke, there is fire, and now I see smoke in front of me. All right. So P implies Q is occurring, and P is also occurring separately. Both are separate events. All right. This is not an event. This is an imaginary situation. Okay, and this is an actual situation. All right. And if these both occur together, then I can conclude that Q is actually occurring. So I am seeing smoke now, and I know the rule that whenever there is smoke, there is fire. So there should be fire now. Okay, so this is inference relation, whereas this is not inference relation. This is one statement. That's all. Okay, so this is called modus ponens. And similarly, there is another inference, well-known inference. Again, I know the law that whenever there is smoke, there is fire. Okay, but now I also know that there is no fire. All right. If there is smoke, there should be fire, and I know that for sure now there is no fire. So I can conclude, right? So imagine these 2 are your 2 premises. This is one premise, this is another premise. From these 2 premises, you are drawing a conclusion. Now I can conclude that there is no smoke also. Okay, so this inference is called modus tollens. All right. Any doubts? No doubts. Okay. So this is the difference between implication and inference. Implication is one statement. Inference is two or more statements related to each other, where the truth value of one will influence the truth value of the other. Okay. In this case, the truth value of P does not in any way influence the truth value of Q. All right. Both are independent truth values. Okay. Fine. And then there is something called distributive law. Like you have distributive law in mathematics, you also have a distributive law in Boolean logic. This is also self-evident. That is, P or Q and R is equivalent to P or Q and P or R, right? Similarly, P and Q or R is equivalent to P and Q or P and R. Okay, so this is self-evident, so I won't explain this. You know this already. All right. Okay, so now let's move on to the next topic in chapter 0, that is definitions, proofs, and theorems. You see, this course, being a theoretical course, it has lots of definitions, lots of proofs, and lots of theorems. All right. So although you know in general what a proof is, what a theorem is, and what a definition is, we will just quickly look at them, quickly revise them so that it's helpful for this course. All right. So what is a definition? A definition is description of an object that distinguishes itself from the rest. Okay, we all know description of an object itself does not make a definition. Like for instance, I can say my pen is black, right? My laptop is black. My table is brown. I can make such statements, but they're not definitional statements, right? A definition should be a description such that it separates this object from the rest. Okay, so such a description is a definition. It defines this object. That is, only this object can satisfy this definition, or any object which has this particular description defines this object is only that kind of object. No other object will satisfy this description. Okay, so you know that already. Yeah. Yeah. Okay. And then mathematical statement. It expresses that some object has a certain property. It may be true or false. right? We know many mathematical statements, something like 2 is an even number, 3 is an odd number, or these are true statements. We can also have a false statement like 4 is an odd number, right? Or there are so many prime numbers between these two numbers, um, or some x is greater than y, where x and y are some specific numbers. Anything, any mathematical statement is a statement about some object satisfying some property or having some property, right? It may be a true statement, it may be a false statement, but it should be basically a meaningful statement or a sensible statement. Okay. Then what is a proof? It is a convincing, logical argument that a statement is true. It should be airtight and beyond any doubt. You know this also. So a proof is a sequence of steps or a series of steps which are logical, where each step follows from the previous one and there are no gaps in this sequence. All right. So it should be evident not only to you, but also to anyone who reads your proof, who goes through your proof. Okay. So that is a proof. It should be airtight. There should be no gaps in the proof. All right. So that is the idea. And then what is a theorem? A mathematical statement that is proved to be true. Generally, we call only some statements of special interest as theorems. Right? So there can be many true mathematical statements. Not all those true mathematical statements are theorems. First of all, they should be proved. Okay, only those true mathematical statements which are proved can be theorems, and even among those, some are of more significance, some are of less significance. Those which are of more significance and of special interest, those are called theorems. All right. There are other true statements which are called lemmas. So what is a lemma? Occasionally, some statements are proved that assist in the proof of others. Such statements are called lemmas. Okay, so lemmas are also true statements. They are also proved, but they are not of special significance. They are true, but they are not that important. But they are useful in proving more important statements. Okay, so such statements are called lemmas. All right, and then we have corollary. New conclusions, drawn easily from theorems are called corollaries. Again, corollaries are also true statements, but they are derived from theorems or inferred from theorems easily. You see, a lemma is used in proving a theorem, whereas a corollary is proved from a theorem, or it is inferred from a theorem. So you can imagine them as byproducts of a theorem, right? So you prove a theorem, and once the theorem is proved, automatically some other statement becomes obvious. That statement is naturally derived from the theorem statement. So those statements are called corollaries. So they are byproducts of theorems. Okay, so the sequence is something like this. So you have axioms from which you prove lemmas, using which in turn you prove theorems, and as a byproduct of theorems you will get corollaries. And now it's not always necessary that to prove a theorem you should always prove a lemma in between. Sometimes you may prove lemmas which in turn help you in proving theorems, or sometimes directly from axioms you can be proving a theorem. Okay, anything is fine. All right, any doubts so far? Okay, yeah. Okay, now whenever you're proving something, there are some things to keep in mind while finding a proof. These are some tips you can say which will help you in finding a proof. Okay, so first of all, the only way of proving the truth or falsity of a mathematical statement is with a mathematical proof. So basically, I may be having a mathematical statement like 2 is even, or the area of a triangle is half BH, or area of a circle is pi r square. I can have many mathematical statements. Now, the only way of proving or disproving those statements is to actually sit down and write a proof. Okay, there is no other way. You have to do step by step. You should start with the axioms. You should start going through the rules, and you should apply those rules on the axioms, and you should try to arrive at your conclusion of either saying that the current statement at hand is true or false. Okay, so it has to be done formally. That's the only way. There's no other way of proving or disproving a mathematical statement. All right. Okay, so let me do one thing. Let me move this to the next page. All right. So particularly when we have some multi-part statements, how to prove them? So for instance, I can have a statement like P if and only if Q, right? This is nothing but P by implies Q, also written as P if Q, right? So this is a multi-part statement because it has two parts, like the if part, right? And only if part. Now, since there are two parts, we need to prove both these parts separately. There is no way in which you can prove this entire statement in one go. You have to break it into two parts, and these are two directions, and you need to prove both the directions. All right. So what does the first part mean? P if Q means Q implies P, or same thing, you reverse the arrow. Still Q implies P only. It's another way of showing it. And P only if Q means he implies Q. Okay. So, okay, I'll explain just a minute. So P if Q means both these conditions. P implies Q and Q implies P. It can be written like this also. That is P by implies Q. All right. So whenever we say P implies Q, okay, we are speaking of two things. One is a necessary condition, another is a sufficient condition. So for instance, if you take an example, again the same example of smoke and fire, smoke can exist only if fire exists. All right, so the very existence of smoke depends on the existence of fire. So smoke cannot exist without fire. So fire is a necessary condition for the existence of smoke. All right, so here Q is a necessary condition for the existence of P. All right. For example, fire. Whereas P, like if you take the example of smoke, smoke is not the cause of fire. Okay. But smoke helps us in inferring that there is fire. All right. But it is not the only means in which smoke can be in which fire can be inferred, right? Like I can look at smoke and I can infer, okay, there should be fire somewhere here because there is smoke. Or I can look at some light and I can infer, okay, some light is coming, maybe there is some fire somewhere. Or sometimes even though there is fire, there need not be smoke. Like fire can be of various forms. The normal fire which we understand is only one form of fire. Other form is like a red hot iron rod, right? That is that also has fire in it, but that fire does not give any smoke. Okay, so that fire we can know either by looking at it, its color is yellow, so we understand that there is fire in it, or if you try to touch it, which is not recommended, but still you will understand that it has fire in it. Okay, so through touch, through look, through its color, or in case it's a fire which gives smoke, that kind of a fire, through looking at smoke, you can infer that there is fire. So there can be various conditions through which you can infer fire. Smoke is only one of those conditions. Smoke is not the only condition through which you can infer there is fire. Okay, so smoke is one sufficient condition. If you look at smoke, it is sufficient to tell us that there is fire. All right. Or if you look at or if you touch it, that is sufficient to understand that there is fire. Or if you look at it, if it is in visible distance, by looking at its color, you can understand that there is fire, right? So any one of these conditions is sufficient to infer the presence of fire. All right. So this is called a sufficient condition. So P is called a sufficient condition for Q, whereas Q is called a necessary condition for P. All right. So P is sufficient condition to infer Q, right? It is not like P has to be necessary for the existence of Q. Smoke is not necessary for the existence of fire, right? Fire comes even before smoke, but smoke can help us in inferring fire. But smoke is not the only thing through which we can infer fire. We can look at it, we can go nearby, we can understand that there is fire through various other means. But for smoke's existence, fire is necessary. There is no other way in which smoke can come. Okay, so fire is a necessary condition for smoke, whereas smoke is a sufficient condition for the inference of fire. Okay, all right. And another example of a multi-part statement is like two sets being equal. Like if you consider two sets A and B, to prove that A is equal to B, you have to prove both the parts. That is, A is a subset of B and B is a subset of A. Okay, you have to prove both these parts separately. Now, we also know what each of these parts mean. So the first part means for all x, if x belongs to A, then x belongs to B. Okay. Similarly, the second part is the opposite direction. If x belongs to B, then x belongs to A. All right. Any doubts? No doubts. Okay. So let's move on. So to prove these statements, some tips like so one tip is find some examples which satisfy the statement. Also, try to find at least one counterexample for the statement. So here, basically what you're trying to do is you're trying very hard to find at least one counterexample for the statement. Assume the statement is true. Now you will not find any counterexample, but suppose you are trying to find at least one counterexample for the statement. Then in the process of trying to disprove the statement, you may find a clue on how to prove it, right? So you may understand, okay, why am I unable to disprove it? Why am I unable to disprove it? So what is not working out may give you a clue on what works out. So it is like trying to approach it from the opposite direction. This is like similar to proof by contradiction kind of a thing, right? You try to disprove it, but in the process you will understand that you cannot disprove it due to so and so reason. So you will understand why it is true. So that may help you in proving it. Okay. So in the process of trying to disprove the statement, you may find a clue on how to prove it, right? That's it. So this is one method. And another method is, rather than trying to find the proof directly, first take some particular examples, in the sense particular special cases. Try to prove that the statement holds for a special case. So for instance, we can take a statement like sum of first n odd numbers is a square number. I don't know if you know this, but this is a theorem. This is a true statement. You take the first odd numbers and add them up, you will always get a square number. So let's say n equal to 3. So let's take the first three odd numbers, that is 1, 3, 5, add them up, you will get 9. We know 9 is a square number. Similarly, say let's take n equal to 6. First 6 odd numbers, that is 1, 3, 5, 7, 9, 11, you will get 36. All right. So that is also a square number. We know that. Okay. So I'll show you the proof later, but the idea is if you take some special cases and see why they are working, you may find a pattern across these special cases and you will get a general idea of the proof for any case. Okay. So sometimes working out examples may actually, working out specific examples may actually give you the general idea of how it is working. All right. So work out multiple special cases to identify the general pattern across these special cases, right? So that is the second method. And a well-written proof is a sequence of statements where each one follows by simple reasoning from the previous statements in the sequence. Right? So this is something which I already mentioned, but proof technically is the same, but sometimes it may not be a well-written proof. All right. A well-written proof should be evident. It should be evident not only to you, but to anyone who looks at it. And there should be no gaps. You see, sometimes you may prove something, but there may be gaps in your proof. Like it may be correct, but there may be gaps in your proof. Like how some particular statement is coming from the previous statements, that may not be clear. So when those gaps are not there, when everything is evident, okay, from this step, next step is following, from these two steps, the third step is following, and so on. When it is so lucid, when it is so easy for anyone to look at it and understand, such a proof is called a well-written proof. All right. Okay. So before we have 15 more minutes before we proceed further, let me take attendance. So I'll take attendance for one of the previous lectures which we missed. Okay. Let me open again. Yeah. Okay. So please scan. I'm showing it one more time. That's it. So do scan this time. Okay, done. Okay, Abhignya, please type your roll number. That's it. Only Abhignya I'll mark, no one else. Yeah. Okay. So let's move on. Once more. Wow, wow, wow. Why? Same for so many people? Okay, I'll just show once more. You try it. If not done, there's nothing more I can do. Okay. I don't understand why Juno app is suddenly not working for so many people. No, I'm not taking attendance of anymore. That's it. No, I'm not taking attendance of anymore. I showed it 3 times. For many people, it is working. You people have joined now. That's why you're asking. I'm not taking attendance. Okay, you keep typing, but I'm not taking attendance of any more people. Yeah. Okay. Yeah. Whoever got error, you post me the screenshot. Only then I'll take. No, you post the screenshot like the student did. That's a good thing. So I'll show one more time in case you are getting an error. You post me the screenshot. Only then your roll number will be considered. Otherwise, I'm not taking attendance. Okay, done. No, I'm not taking your roll numbers without you posting the screenshot. That's it. I showed 4 times, not more. Okay, let's continue. Okay, so uh, we have looked at some tips on how to prove different theorems. So now let's look at different kinds of proof methods. So I mentioned them once in the class, but now we will look at examples. So the first method is proof by construction. So let's take the example of the very well-known theorem, Pythagoras theorem. You all know this theorem, but not many of you may know its proof, like why and how this statement is proved, right? So we'll look at that proof today. A square plus b square equal to c square, where a, b, c are the sides of a right angle triangle with c as the hypotenuse. Okay, so there are actually more than 300 proofs for this single theorem. All right. People have come up with various ways to prove this theorem. We will look at one particular proof today, but just to let you know that there are many proofs for this theorem. All right. So what we will do, we will construct a special square out of this triangle by replicating this triangle 3 more times. So we will have 4 triangles in total, and using these 4 triangles, we will construct a special square. So once we construct that, we will use it to make our point. We will use it to prove the theorem. All right. So what we will do, so first let me draw the outer square. Okay, so let's assume the triangle is arranged like this. Okay. So suppose if this is A, this is B, then this is C. Right, or let me put it here. This is C. And again, this is A, this is B, this is C. Now, sorry. Okay, again, this is A, this is B, and this is C. Okay, this is A, this is B, this is C. Now, there are again steps to prove that the inner one is also a square. I'm not getting into those steps, but the inner one is a square. Okay, the diagram it may not look exactly like a square, but it is a square. So just take my word for it for now. So we have an inner square and we have an outer square. All right. So OS is outer square and IS is inner square. So as we can see, the area of the outer square is the area of the inner square plus 4 into area of the triangle, right? There are 4 triangles. So area of 4 triangles is nothing but 4 into area of each triangle. All right. So we will use that equation to prove the theorem. So area of outer square is equal to area of inner square plus 4 times the area of each triangle. Okay. And what is area of outer square? Each side squared, right? So what is the length of each side? A plus B. You see, each side is same. A plus B, A plus B, A plus B, A plus B. So A plus B times A plus B, that is A plus B whole square, is the area of the outer square. And what is the area of inner square? Inner square side is C. So C square plus 4 times area of each triangle. Each triangle is a right angle triangle. So it is half AB, half base into height. Half AB. Okay, so let me strike off this. And now let me expand this. So this will be A square plus B square plus 2AB is equal to C squared plus 2AB. Right? So this will cancel out. So we got our statement. A squared plus B squared equal to C squared. That's it. Hence proved. So you see, This is a proof by construction. So to prove the statement a square plus b square equal to c square, right, what we did, we somehow sort of constructed some new shape, a new geometric shape, a square, these triangles arranged in some particular way, and all that. We cooked up this geometric shape, and we use that to prove what we want to prove. Okay, but we actually did construct the proof. We did not prove it by coming from the opposite direction. Okay, let me assume this is wrong, then where will I land up? No, nothing like that. Here we actually constructed a special shape, and in the process of solving an equation related to the special shape, we proved step by step that our statement holds. Okay, we derived our statement. All right, so this is a proof by construction. Okay, and you should actually look up a book called QED Beauty in Mathematical Proof. All right, so this is a very small book, it's hardly 40 pages or something, and it gives visual proofs of many of the mathematical statements which we know, like area of a circle, it proves area of a circle, area of a cone, volume of a cone, area of a pyramid, volume of a pyramid. So all those kinds of things, a tetrahedron, those kind of things. And it proves in just 2 pages. Actually, in one page is just description and another page is the proof. Okay, so every proof, every statement is allocated only, every mathematical statement, every theorem is allocated only 2 pages. One page, the description of the proof, and one page, the proof. And the proof is visual. It's an excellent book, and it makes you think of mathematics or mathematical proofs in a very different way. All right, simple visual proofs for most of the statements we know, but whose proofs we may not know. All right, so it's a very nice book, as the title says. It shows that mathematical proofs are beautiful. Okay, and it shows many such constructions. And as you can notice, it's not evident or it's not automatic to come up with such a construction. All right, a lot of ingenuity and a lot of creativity is involved in thinking of such a construction. So that is the reason why mathematical proofs, although they are related with mathematics, which is such a systematic thing, it is not so easy for anyone and everyone to prove them. You need a lot of creativity and an artistic bent of mind to prove these theorems. So maths and the proofs in maths are as much an art as they are science. All right, similarly, even computer science and even computer programming involves a lot of creativity. It's not like given a problem, you can automatically or mechanically come up with a program to solve that problem. All right, a lot of ingenuity and creativity is involved. You need to construct the program. Okay, so you should also look up this book called The Art of Computer Programming by Donald Knuth. This is considered to be the Bible of computer science. Actually, it's not one book; it's a volume. It's a series of some 3-4 volumes, um, and it is very dense. Okay, so it will be difficult for you to finish even one volume, but at least just go through some sections. All right, and he is also the father of LaTeX language, the typesetting language using which you can write research articles and even prepare PPTs, presentations. It's an excellent language. So look up this book also. It will be very useful. All right. So what I'll do, I want to move on to the next one, but I'll stop here for now, and let me know in case you have any doubts. Okay. All right. So if you have no doubts, then we'll stop here. Okay. Okay. Let's stop here. I'll see you on Monday.